In this video, we will learn how to derive demand functions for Cobb Douglas and Leontief utility functions. Okay, so let us say we are being given this Cobb Douglas utility function where utility is equal to x1 into x2. X1 and x2 are the two goods. Okay, so this is our Cobb Douglas utility function. Let us write the budget constraint something like this: price of good 1 times units of good 1 plus price of good 2 times units of good 2 should be equal to the total income. Okay, so we want to maximize this utility subject to this budget constraint, and then we will derive the demand functions. Okay, so first step is, we set marginal rate of substitution equal to the price ratio. Okay, marginal rate of substitution, we set it equal to price ratio, and also we construct the graph here. Okay, so let me show it graphically also to make a sense here. So let us say this is our budget constraint. X1 good is here, x2 good is on this axis. Okay, so marginal rate of substitution should be equal to the ratio of the price. Okay, so what is the coordinate of this point? If this is the budget line, what is the coordinate of this point? At this point, when we put x2 is equal to 0, okay, so this whole stuff becomes 0. That means x1 is equal to m upon p1. So here we will have m upon p1. Okay, all income will be spent on good one. And what is the coordinate here? Simple, put x1 is equal to 0, so x2 will be equal to m upon p2. Okay, so at this point all income, sorry, all income is spent on good x2. Marginal rate of substitution means simply marginal utility of good 1 upon marginal utility of good 2 should be equal to price of good 1 upon price of good 2. Okay, and our indifference curve will look like this. Okay, this is our indifference curve with a given, we want to maximize our utility with the given budget. So when the budget line and indifference curves are tangent to each other, that is when this condition is satisfied, we are at equilibrium position. Marginal utility of 1 means derivative of utility function with respect to good 1. Okay, this comes out to be, take derivative of this utility function with respect to x1. So derivative of x1 is 1, we are left with x2. Similarly, du upon dx2 means taking derivative of this utility function with respect to x2. So taking derivative of x2, so it will become 1, so we are left with x1. Okay, simple stuff. So using this very situation, marginal utility of good 1 is being shown by this thing, and marginal utility of good 2 is shown by this thing. So marginal utility of 1 is equal to this, and we got it as x2, and marginal utility of good x2 is this du upon dx2, which comes out to be x1. It should be equal to the ratio of price p1 upon p2. Solve for x2, so x2 is equal to p1 upon p2 into x1. Okay, now just plug this value of x2 back in our budget constraint. Okay, if I put it in the budget constraint, what will I get? So we have p1 x1 plus p2. The value of x2 is this, what is it? It is p1 upon p2 x1. It should be equal to income. Okay, so here p1, sorry, p2 and p2 will get cancelled. This thing and this thing will get cancelled. We are left with p1 x1 plus p1 x1 is equal to m. That means twice p1 x1 is equal to m, which gives us x1 is equal to m upon 2p1. So this is the demand of good x1. Okay, demand for good x1, and here at a point where indifference curve and budget line intersect. Corresponding to this, we get the optimal demand is m upon 2p1. Okay, symmetrically we can say, or we can show that here demand for good x2 will be equal to a lekta malak drama, it will be equal to m upon twice p2. Okay, so you can just use this, just plug this again in the budget constraint to get the value. Okay, so let's put it in the budget constraint. uh, so I should you know how to calculate then this. Okay, so if x1 is equal to this, so let me also show it here. So we have p1 x1 plus, sorry, p1, what is the value of x1? We got it as m upon 2 p1 plus p2 x2 is equal to m. Okay, so we have here m m sorry, why we don't have m here? So this p1 and p1 will get cancelled. Okay, so we are left with m upon 2 plus p2 x2 is equal to m, which gives us p2 x2 is equal to m. Transposing this here, it will become minus m upon 2. So this is p2 x2 is equal to 2m minus m is only m upon 2. That gives us x2 is equal to, you know, m upon transposing this, it will get divided p2. This is the demand function for x2, which I was telling you that it will be here. Okay, so I also calculated it to make the things, you know, simpler. So this was about the Cobb Douglas utility function. What about the Leontief preferences? How do we solve this kind of question? Let us say we have budget like this: p1 x1 plus p2 x2 is equal to m. Okay, we want to maximize utility subject to this budget constraint. Okay, now the utility maximizing bundle will lie where our, you know, budget line meets this kind of utility function. Okay, to solve this kind of question, what we do, we don't use the Marner rate of substitution, we don't take the derivatives because it is not differentiable at all points, this min function. Okay, what we do when we are encountered with this min case type function, we simply equate whatever is in the bracket. So in brackets we have minimum of x1 x2, so let us equate them. That means x1 is equal to x2. Okay, now put this value in the budget constraint. So x1 is equal to x2, so we have p1 in place of, let me write it here, x1 plus p2 in place of x2, I will write x1 will be equal to m. So we have, taking x1 common, we are left with p1 plus p2 is equal to m, or x1 is equal to m upon 2, sorry, transposing this, p1 plus p2. Okay, this will be the demand for good x1 when we have Leontief preferences. Okay, similarly or symmetrically you can calculate for x2. That will be same, that means x2 will be equal to m upon p1 plus p2. Just substitute this back in demand function, you will get. Rather, since x1 is equal to this, we know x1 is equal to x2, that means x2 will be also this m upon p1 plus p2. Okay, now how does the graph look like in case of perfect complements, what we call Leontief preferences? So this is our budget line. Hey, this is our budget line. Okay, so we have x1 here, x2 here. So this is a coordinate where all income will be spent on x1, so m upon p1. So here this is m upon p2. Okay, and we also got x1 is equal to x2. So our ray will look like this. Okay, 45 degree in this case, and the indifference curve in this case will be something like this. Okay, so at equilibrium, this is our indifference curve. Our indifference curve will meet the budget line at its kink. That means the corner of the indifference curve will touch the budget line in case of, you know, perfect complementary utility function when we try to maximize it. Okay, so demand function in case of perfect complementary utility function was that the demand for good was a function of income and price of good 1 and price of good 2. Okay, so demand for good 1 is function of three variables, that is income, price of good 1 and price of good 2. But in case of Cobb Douglas utility function, demand for a good was a function of only income and its own price. Okay, so you can see the difference here. In case of Cobb Douglas utility function, demand for good was a function of income and price of this good itself, not on the price of other good, what we call x2. So this is the basic difference between the Cobb Douglas utility function and what is the demand function, and about the Leontief utility function, what we call perfectly complementary utility function also. Okay, so in case of Leontief utility function, demand for x1 here depends on income, price of the two goods. But in case of Cobb Douglas, it is only the demand for it depends only on the income and its own price. Okay, so mm, where should I show the demand function for good 2? So this was for good 1. So symmetrically x2 which I calculated was equal to m nar lagun yer x2 was m upon 2p2. Okay, so these were the demand functions for Cobb Douglas preferences. These two are the demand functions for Leontief or min functions. Okay, thank you.